Okay, so this is example 2 in solving separable differential equations with initial conditions, first order. So we have the derivative dy over dx, dy dx, equals x divided by y. So this is the description of what the derivative looks like for some kind of initial function. We're going to find y, okay? That's our job, find y. And we want to find the particular solution because we're given initial conditions, right? If you remember what you know about slope fields, right, you can find a general antiderivative or an integral that has some constant, you don't know what it is, but when you're given initial conditions, there's only one graph that would fit that would pass through that point. So now I put a little note down here, and I'll explain what this means a little bit later. There's a bit of a reminder for me to touch on that here today. But separable differential equations. So you should know a little bit about how to start this. We understand that this is not a fraction, but it sort of can be separated, treated as a bit of a ratio. And so what we do is we, in fact, do that. And what I'm going to do is I'm going to bring this dx over here, and I'm going to bring this y over here. And it's going to look like this. Y dy equals x dx. So this is a pretty easy one. We've got all the y's on one side and all the x's on the other side. And now we integrate both sides, right? Integrate both sides, and so that means you find the antiderivative of this. And this is going to be 1/2 y to the 2, because you add 1 to the exponent and you divide by that new exponent. So it's 1/2 y squared. Over here it's going to be the same, 1/2 x squared. Okay, we good so far? All right, so we have to remember that we have to add a constant, because when you integrate, there's going to be some constant. And we're going to find out what that constant is right now when we substitute these initial conditions. Now, the late c, let me explain what the late c means, okay? Sometimes students leave the solving for the constant, they leave that till later. And they do all sorts of, well, we're going to multiply this by 2, so I'm going to have y squared. Okay, don't write this down, but this is what they do. And we 2c, and then I'm going to square root, square root of this, x squared plus 2c. And then they get into a bit of a mess here, like now you have to solve for c with x and y. It doesn't work that way. You have to solve for c right away, and then you can go ahead and find y. A, it's difficult to do this, right? B, there's some of the mathematical things that happen in there that are going to skew things, so you can't do that. That's the late c, so you do not want to solve for y without having solved for c first. Okay, so we'll continue. So 1/2, the y value is 1, and the x value is 0. And so we have, I guess, what do we have? 1/2 here equals c. So the c value is 1/2. Well, that's great. Now what you can do is you can go ahead and you can substitute that 1/2 in for the c. I'll just erase this to save some room. And we'll put that here. That was 1/2, right? 1/2. Did everyone see how I solved for that c and got 1/2? This one maybe is a bit easier than the first one I did with you, but it's okay, we got a tough one coming up, don't worry. And now we solve for y, very similar to what we did before. We'll multiply everything by 2, right? Multiply everything by 2, take the square root. Now, is this positive or negative? Positive, thank you. Yeah, I remember from last time. Look at this. When f is 0, y is positive 1. We know it's positive. So if I put a 0 in here, I get the square root of 1. And would it be positive or negative? Well, the initial conditions tell us it must be positive. So it's the positive version. We don't have to write anything there. And that is this is the exact function that would give us x over y as a derivative. And if you plug in 0 here for x, you get 1 for y. So it satisfies all those conditions. Okay, any questions on that?